Welcome back everyone. In this lecture we will try to prove the denominator identity. Before that we need to prepare some results. Let us begin with one small lemma. So we want to rewrite the product side of the denominator identity as follows. So this is just to emphasize what is going in the product side. So let us recall what is the Weyl vector. The Weyl vector is defined to be rho, so which is in terms of the fundamental weights given to be summation omega I, which is also in terms of the positive roots it is half sum of positive roots. So in particularly we have the following observation. So omega of hi is 1 for all I ranging from 1 to n. In particularly Si of rho is going to be exactly rho minus alpha I, and this is also true for all I range from 1 to n. So this is the most important thing. So we will actually use this to compute what will happen to W rho minus rho. Okay. So that is what involved in the sum product side of the sum side of the denominator identity. So anyway, if we actually rewrite the product side, so let us actually look at the product side. Let us call it pi. So this is the product side of the denominator identity. So what is this? This is exactly equal to e power rho product 1 minus e power minus alpha in delta plus. So this is the product side. So what we can do here, so we can actually simply rewrite this as follows. So if I take this pi, so if you actually take out this e power minus alpha from this product, then you get e power rho times product e power minus alpha e power alpha minus 1 alpha in delta plus. So now if we just simply collect them together, we can see that this is e power rho times product. So this thing will come out. So let us first take it out. So then you get e power minus summation alpha in delta plus. So this is what contributed from this particular element. So then you can see that times product e power alpha minus 1 alpha in delta plus will come. So this is just a way of rewriting things. So now note that rho is nothing but half sum of positive roots. In particularly twice rho is just a sum of positive roots. So if we just substitute this in this equation star, so then we get exactly e power minus rho times product e power alpha minus 1 alpha in delta plus. Okay. So the product side of the denominator can be rewritten this way. So now to prove the denominator identity, we need to use the Weyl group action. So in order to understand it, so let us actually first understand the Weyl group action on the Euclidean space that is there underlying this H star. Okay, recall. So we have this H star is given by, so this is span over C of alpha i's, I range from 1 to n plus 1. So if you want to write it in terms of epsilon I basis, so this H star can be identified as C epsilon 1 plus etcetera plus C epsilon n plus 1 with the relation that epsilon 1 plus etcetera epsilon n plus 1 being 0. So this is how one can identify H star. Okay. So now what we are going to do, we are going to actually take the real span of this. So indeed the real form, okay, since the inner product alpha I alpha j, they are all integers. So we still get inner product on the real span of alpha i's. So in particularly that inner product will make that HR star to be Euclidean space. Okay. So let us take the definition of E to be this. So E is defined to be HR star, which is the span of all these alpha i's over real I ranging from 1 to n. Sorry, this is I range from 1 to n. So, recall what is alpha I. So, alpha I is nothing but epsilon I minus epsilon I plus 1 in terms of epsilon I basis. So, we have this real space. So, this is a real space whose dimension is obviously n, because alpha i's are linearly independent over C. So, they also linearly independent over R. So, now if we take this space, the same inner product descends to inner product on this space E. So, recall what is the inner product on alpha I alpha j. So, this is exactly 2 if I equal to j, and this is exactly minus 1 if j equal to I plus 1 or I minus 1 and 0 otherwise. So, this is the inner product we have between alpha i's. So, the same inner product we can take it in the real space as well. So, now that makes, okay, I will leave it to you to check. So, this makes E as Euclidean space. So, E with this inner product is indeed Euclidean space. So, the meaning of Euclidean space is that this inner product is indeed here, in this case it will become positive definite form. It is a non-degenerate symmetric bilinear form which is also positive definite. That means, if you take some lambda which is non-zero from E, then lambda lambda must be always positive. Okay. So, that is actually kind of one can check quickly, because if I take lambda inside E, so lambda can be written as, let us write it in the alpha I basis, then this is exactly C 1 alpha 1 plus etcetera plus C n alpha n. Now, if you rewrite this in terms of epsilon I basis, so this exactly becomes C 1 epsilon 1 minus epsilon 2 plus etcetera plus C n epsilon n minus epsilon n plus 1. So, recall this inner product indeed obtained from the inner product of epsilon i's. So, the epsilon I epsilon j, so this is, we know this is the canonical delta I j. So, this is the inner product we had it in the ambient space, then that induced the inner product on the H star. So, that is the inner product that we are actually taking here. So, it is enough to compute it in terms of epsilon I basis. Then if you compute this lambda lambda in terms of the epsilon I basis, you can see that this is exactly equal to C1 sorry C2 minus C1 epsilon 2 C1 epsilon 1 plus etcetera whatever it is. So, then here you get minus Cn epsilon n plus 1. But if lambda is non-zero, then one of the coefficients here it will be non-zero. So, that is for sure. So, then if you actually look at in terms of epsilon I basis, so if you write this as some di epsilon I summation I range from 1 to n plus 1, then lambda lambda is indeed summation di square, which is always positive whenever one of the di is non-zero. So, that is what makes this as Euclidean space. Okay. So, one can also straight away check that with this inner product as well, we have positive definite form. Indeed, if you write it in terms of the matrix, it will be a positive definite matrix. So, the matrix entries being the inner product alpha alpha j. So, this is all just aside. So, that indeed gives us Euclidean space on which we can talk about the symmetric group action. So, that is all important. So, now if you recall what is SI, SI is defined from H star to H star as an operator. SI of lambda, it is lambda minus lambda of Hi alpha I. So, we also actually identify this with the inner product, then this is also same as lambda minus twice lambda alpha I divided by alpha I alpha I alpha I. So, indeed SI is a reflection with respect to this vector alpha I. So, you take this hyperplane perpendicular to this alpha I, then it is reflection with respect to that hyperplane. So, it makes more sense to consider these reflections in the Euclidean space. So, we will actually define similar operator on this E. So, again we call it SI. So, basically we are taking the restriction of these operators on E. So, these operators again defined to be the same formula. So, SI of lambda equal to lambda minus twice lambda alpha I divided by alpha I alpha I alpha I, and it is not hard to see this SI square will be identity on E. So, in particularly SI they are all invertible operators on E. Not only that, if I take this H alpha I to be the hyperplane which is perpendicular to alpha I, this is those lambda in E such that lambda of alpha I is 0, then it is clear that SI is reflection with respect to this hyperplane H alpha I, because the elements of H alpha I will be fixed and alpha I will be sent to minus alpha I. Okay. So, SI of lambda is lambda if lambda alpha I is 0, that is clear, and SI of alpha I is going to be minus alpha I. So, this is what defines the reflection. And in the usual action of Sn plus 1, this reflection is indeed identified with the transposition II plus 1. So, we have this natural map, okay, from this Weyl group, okay, we take W to be the Weyl group generated by SI, where this SI comes from this GL of E. So, this is how I am now going to look at it. So, these are all operators on E which are invertible operators, indeed they are reflections. So, you take subgroup generated by this SI for I range from 1 to n. Okay. So, this is the subgroup that we are interested in, we call this as the Weyl group, and this Weyl group naturally isomorphic to Sn plus 1. So, this is something we have seen already, and what this Si will corresponds to inside Sn plus 1, this will corresponds to the transposition II plus 1. So, you take the transposition II plus 1, so that is what transposition will corresponds to this Si, and we know that the transpositions II plus 1 will generate Sn plus 1. So, that is why this W becomes isomorphic to Sn plus 1. Note that the action of Sn plus 1 on E is also is a faithful action, because there are no fixed points there in E. So, now we also have reflections corresponding to each root of root comes from delta. Okay, recall the set of roots of G, the set of roots of G which is SLN plus 1 again with respect to the carton H. So, that is identified with epsilon I minus epsilon j, where 1 less than or equal to I less than j less than or equal to n plus 1. So, if we take alpha in delta, so in particularly one can take it from the delta plus, because delta is nothing but delta plus disjoint union minus delta plus. So, the reflection that is defined with respect to alpha and defined with respect to minus alpha will coincide. So, because of that one can just restrict to alpha in delta plus. So, for alpha in delta plus again we can define the reflection as before from the Euclidean space to Euclidean space, which is given by the same formula S alpha of lambda equal to lambda minus twice lambda alpha divided by alpha alpha alpha. So, if you take this as definition, it is not hard to see that this S alpha will corresponds to the transposition I j inside Sn plus 1. Indeed, here is the star exercise. Okay, it is not very hard, but it is actually required some understanding of this reflection subgroups. So, this actually says if you consider all possible reflections in the reflection subgroup W. Okay, so, the set of all reflections from W. So, this is something we can actually talk about, because W is generated by reflections SIs. So, we can talk about all possible reflection that comes from W. So, this must be equal to this S alpha alpha from delta plus. So, this is actually somewhat non-trivial fact to prove. Anyway, this fact is not needed, I am just quoting it here as exercise. So, here we have very explicit identification. Whenever we take S alpha, alpha is being epsilon I minus epsilon j. So, then for this particular positive root, the reflection corresponding to this is nothing but the transposition I j. Note that these transpositions also generate the group. Okay. So, one can ask this natural question, okay, because we have some set of generators. If we actually have those generators, then what will be the relations that actually we have to impose, so that this group is actually isomorphic to the group generated by those generators modulo that relations. Indeed, it is aside, it is also like very hard exercise, maybe I will state it as star exercise. One can actually say that this order of the relations among this SIs that can be easily read off from the Deniminator diagram. So, recall the Deniminator diagram is nothing but you have 1 to n and then this is the path P n, okay, 1 and 2 there is an edge, 2 and 3 there is an edge, and this is actually drawn using this data, the inner product alpha I alpha j. Whenever alpha I alpha j is the inner product is 0, you do not put any edge, and alpha I we do not put any edge, we just take it as vertex alpha I. Then alpha I alpha j you connect by an edge if the inner product is non-zero, which is exactly minus 1. So, now from this you can see that it is not hard to see Si Sj. So, this will commute whenever j is different from I plus 1 and I minus 1, and Si square will be identity. So, W is generated by Si modulo these relations. So, these are all the relations. The relations Si square being identity and Si Sj commutes, and we have this bride relation which is comes from the order of Si plus 1. If you take Si plus 1, the order, because that is going to be cycle of length 3. So, the order of that will be 3. So, Si plus 1 power 3 must be identity. Now, using this Si square being identity, you can rewrite this. So, if you rewrite this, this is exactly Si plus 1 Si equal to Si plus 1 Si plus 1. So, this is what called bride relation. This is what called bride relation, okay, and W is indeed isomorphic to group generated by Si modulo these relations. Okay, these are all the natural relations among SIs, and those relations determine the group. Okay. So, indeed you have to show that if you take group generated by Si modulo these relations, that group is finite group and it has exactly the cardinality of Sn plus 1. So, I will leave it as exercise, okay, because these facts will not be needed in our course. So, now we actually try to understand the Weyl group action on the Euclidean space. For that we need to actually understand how it is acting on what are called chambers. Okay. So, the Weyl group action on E. So, this is something very interesting. Okay. So, basically Weyl group being the phyloid group, that is Sn plus 1 acting on E, you can see that we can define the fundamental region for that. Okay. So, we are actually trying to find out what is that fundamental region. So, we will actually give very explicit description of that. So, now note that, so this W, which is Sn plus 1, acts on the set of roots. So, that is clear, okay, because the set of roots. So, this is something we proved using SL2 theory. So, now if you take this action, so then it is clear that using this action you can also get the action on this union of hyperplanes. The union of H alpha comes from delta. So, now note that H alpha is same as H alpha is same as minus H alpha, sorry, H of minus alpha. So, indeed this set you can think out as union over H alpha in delta plus, but delta plus is not invariant under W. So, that is why we want to replace something that is invariant under W. So, that is why we are keeping this delta here. So, now it is clear that W acts on this union of H alpha. So, that just follows from the formula, because H alpha by definition this is those vectors inside your Euclidean space such that V comma alpha will be 0. So, these are all the hyperplanes, of course defined using alpha. Now, if I start with V in H alpha, sigma is in W, then sigma V, we want to say that this will be in some other hyperplane. So, but you can see that sigma V comma alpha is going to be equal to sigma V sigma alpha. That is easy to see, because this Weyl group Sn plus 1 that will actually preserve this inner product, that is something you can directly verify. So, using that you can see that this V comma alpha is same as the sigma V sigma alpha. So, that tells you that this is sigma V comma beta for some beta, which is sigma alpha, which is in delta. So, that means sigma V is inside H of sigma alpha. So, this tells you that W acts on this union of H alpha. But note that as a topological space, E comes with the natural topology, comes from the inner product, you can identify with Rn, not a problem. So, that standard topology if you use, these hyperplanes are given by some single equations. So, they must be closed subsets. So, basically delta being finite set, this is indeed a closed subset of E. So, this is the topology that we get it on this subset. So, then if I take this complement, so look at this complement E difference union H alpha in delta. So, W will act on this also. So, W acts on the complement, because W acts on the union of H alpha. So, it must act on the complement as well, because W acts on E, because W is being subgroup of GL of E. So, now what is about this set? So, this set is, you can easily see that. So, this is nothing but open and this is convex, that is easy to see, because H alphas are like hyperplanes. So, one dimensional less. So, if you take union of them and then take the complement, so you will get actually huge open set which will be a convex set. Okay. So, this is something very elementary, it comes from the Euclidean geometry, I am not going to prove it here. So, now we can actually look at these open convex set. So, they will be just it may not be connected, it is not actually connected, because every time you are removing the hyperplane. So, whenever you remove the hyperplane from the space, so if you just remove, let us say some hyperplane, let us say passing here. So, then the space will become two parts. So, the like we can talk about the positive side and negative side if it is defined with respect to alpha. Let us say this is H alpha, then alpha positive and alpha negative will be the two sides of the complement of this hyperplane. So, then it is easy to see that the both of them are two connected components of this H alpha. So, if you remove one hyperplane, you get already two connected components. If you remove finitely many of them, then you will get finitely many connected components. Okay. So, here you have open set which is convex, which can be written as union of connected components. And since because this set, okay, let us call it capital X, this is itself convex. So, the connected component of this also will be convex. So, those connected components will be called chambers. The connected components of this X are called chambers of E. So, we are interested in understanding the Weyl group action on these chambers. So, naturally the Weyl group act on the chambers, because the Weyl group actually takes one connected component to another component, because Weyl group action is continuous. Okay. So, Weyl group acts on this C, which is the set of chambers of E. Of course, it is all with respect to the Weyl group action. Okay. The chambers defined using the Weyl group action, and then we have the Weyl group action on the chambers. Now, we want to understand what is this action, how actually the W is indeed acting on these chambers. So, let me make the proportion. So, I will actually try to prove most of it. Before that, what we will do, we will actually identify one particular chamber with respect to this alpha i's, we call it fundamental chamber. Okay. So, here is the definition of chamber, and here is the first observation that we make. So, these are all some simple observation, I am not going to prove it, it all comes from the convexity. So, if I start with 2 points, so if I take 2 points of this X, so I am going to look at it when they lie in the same chamber. Okay. They lie in the same chamber, they lie in the same chamber if and only if. So, you look at the reflecting hyperplane, which is H alpha. So, you have actually just removed that H alpha from the Euclidean space, and if these 2 points actually lie in one of the chamber, then they must lie on the same side of the hyperplane, there is no other option. So, it is very clear from the geometry that these points lie on the same side of each reflecting hyperplane. So, this is something very simple observation. So, now using this we can actually see that the following set is indeed chamber. This is those vector in E such that when you take inner product with alpha I, that must be positive for all I 1 to n. So, now in terms of the coefficients, what it is, if you write V in terms of this epsilon I basis, then this is C 1 epsilon 1 plus etcetera C n plus 1 epsilon n plus 1, then you can easily see that V comma alpha I is nothing but V comma epsilon I minus epsilon I plus 1, which is exactly C I minus C I plus 1. So, we demand that this is positive for all I. So, that says that C 1 must be greater than C 2, must be greater than etcetera greater than C n plus 1. So, this is the inequality that we get when you take this fundamental chamber. So, this C is called the fundamental chamber. So, we will prove in a minute this is indeed chamber, and the action of the Weyl group acts on the set of all chambers simply transitively. So, you will be able to get all other chambers by applying the Weyl group element on C. So, now let us actually look at why this is indeed chamber. So, if I actually look at the closure of this chamber, from the definition it is clear that this will be just you take all the vectors in E such that V alpha I is greater than or equal to 0 for all I 1 to n. So, in particular if you want to write it in terms of this coordinates, then V if you write it in terms of C 1 epsilon 1 plus etcetera plus C n plus 1 epsilon n plus 1. So, then this C1 should be greater than or equal to etc. greater than or equal to Cn plus 1. So, this is how you define this C bar. So, now how one can actually think about this chamber, okay, why this is first of all chamber. So, note that if we take 2 points from x, if they lie in the same chamber, then they must lie on the same side of the each generating hyperplanes or reflecting hyperplanes. So, in particularly here we have defined V alpha I being greater than 0 for all simple roots. So, if I take alpha from delta plus, you know that alpha can be written as summation ni alpha I with ni greater than or equal to 0. So, this forces that if V is from C, then V comma alpha is also greater than 0, because one of the ni should be non-zero. So, this says that if you take V in C, then V must lie. Okay, if you take 2 points V dash from C, they both lie on the same side of the defining this reflecting hyperplanes. So, this C is clearly open and connected and convex. Okay. C is open plus connected plus convex, that is obvious. Now, using this you can see that C must lie inside some chamber. So, this is for sure, because C is connected. So, it has to lie inside some connected component. But if you have anything that is bigger than this C, okay, let us say some vector you take from C dash difference C, then it is clear that for this vector there exists I from 1 to n such that V comma alpha I must be less than 0, because V comma alpha I cannot be equal to 0, then it will lie in the hyperplane, but we are working in the complement because this is all happening inside x. So, this V alpha I must be less than 0. So, then this is a contradiction, because if this C, okay, is indeed non-empty, because C is given by all this C1 etc. Cn plus 1, which satisfy this inequality C1 greater than etc. greater than Cn plus 1. You can actually take any real numbers like this. So, these Ci's are reals such that this inequality should be satisfied. So, that means C is non-empty, but we know that if 2 points lie in the same chamber, they must lie on the same side of the hyperplane. So, then this point and the point in C, they now lie on the different side of this hyperplane that is defined by this alpha I, which is a contradiction. Okay. That proves that we will not have this strict inequality. So, we must have equality. So, this is supposed to be equal. So, this proves C is indeed one of the chamber. Okay. So, we will actually use this Weyl group action to understand how it acts on the chambers. So, we will indeed prove that the action of the Weyl group on this set of chambers will be simply transitive. So, we will actually do that in the next class. I will stop here. Thanks.